Hacking, a brief primer on reverse engineering Bluetooth transmissions. All right, so just going to briefly go over an overview. We have who am I, getting started, some OSINT resources for Bluetooth and IoT devices, brief history in Bluetooth, some select tools for Bluetooth IoT analysis, some tools for Bluetooth sniffing, a section called Medical Information at Risk. You'll have to wait to see the contents there. Trial and error, reverse engineering, BLE transmissions, and Android application secrets. So if we have time to get through all these slides successfully. All right, so who am I? I'm actually a junior security analyst at Sidara and former managed Wi-Fi technical support representative. I like more than software bugs, and this is actually my backyard fence. I have a lot of hobbies way outside the scope of this talk, but yeah, Prey Mantis is one of them. All right, so getting started, we have some pretty basic information here. Should be self-explanatory to a lot of people here. When you're going after a device, I want to get right to the meat of it. So you definitely want to recon the attack surface. A lot of time can be wasted when a few more Google searches can get you there. Utilizing open source intelligence and having a clear mission, once again, pretty self-explanatory, but the amount of devices I bought without a clear agenda for what I wanted to do with it has kept me scatterbrained for a while, so I would definitely keep your eye on the prize in that respect. All right, so more about these open source intelligence resources for Bluetooth and just devices in general. One of my two favorite resources would be the FCC directly, along with Google. And you can find this one website, fcc.io, through Google search. And as it states here, they are required for all wireless emitting devices sold in the United States. And honestly, you can get a wealth of information, internal, external diagrams of the device, where you can take a look at the chips if you want to do any desoldering or anything along those lines. But fcc.io is a great resource and will have a surprising amount of information. Oftentimes, due to things like radiation, all devices have to meet certain specifications. So a lot of stuff that won't appear in a manual, which is very little at all in modern manuals, you can get right off this website. I'm going to show in a second. All right, little hiccup there. All right, so now this information was scraped directly off fcc.io. In this case, this is actually going to be one of the devices I'm going to be speaking about, referring to medical devices, and these are the internal schematics. We're going to talk more about this device, but right away, I didn't even have to open up the device. In fact, the device I'm going to be demonstrating, this particular device, I didn't open up at all. But I was able to get a lot of information right out the internal specs. I get to see the type of chip that was being used, and along with some of the other reports, you can just get a good visual, look for potential debug ports like UART. In this case, those in particular are not applicable, but I got a lot of information without ever touching the device, as you'll see moving forward. So now I just want to go over a brief history of Bluetooth, and this information was summarized directly at Bluetooth.com, but I'll go ahead and just reinstate it. So what is Bluetooth? It's not an acronym and doesn't stand for anything, so what does it mean? The name actually dates back to the Viking era, specifically King Harald Gormson, who earned the nickname Bluetooth, essentially due to a rotting tooth, which had that color. And apparently he's also known for unifying Denmark and Norway in 958. And it's essentially a combination of two runes. I won't try to pronounce these because I'll butcher them, but they together form the Bluetooth logo. And it looks like that little colon, it didn't render my PowerPoint correct, but yeah. So, sorry about that. All right, so like I said, this is a brief primer, so a lot of these nitty-gritty details, unfortunately, you're not going to get that from me. But we're going to start this intro just comparing Bluetooth Classic to BLE. Bluetooth Classic, well, Bluetooth in general is a specification. There's a lot of versions. We're currently up to 5.3. Oh, I'm sorry. All right, can everyone hear me better? All right, sorry about that. So the Bluetooth specification, we're currently at version 5.3. And one thing to keep note is that What's often referred to as Bluetooth Smart starts at version 4.0. It's when security started to get a lot better. Majority of devices are still running 4.0, and we've had that spec since 2016. So as of right now, even the device I'm going to show, the chip was compatible with 5.3, but the Bluetooth version was set for 4.0. So even newer chips are still using old protocols, and that's essentially part of the problem. Another thing about Bluetooth is that I'm sure a lot of you are familiar with is that in terms of the wireless spectrum, it uses the same exact frequency range as Wi-Fi, starting at 2.402 to about 2480. And part of the reason part of the issue with Bluetooth in terms of interference between signals, it'll do something called frequency hopping. So essentially there's 3 advertising channels and there's 36 data channels. And when a device is getting, okay, so I'm gonna just a preface. Bluetooth operates on a client server model. So you have a device speaking here trying to connect from point A to point B. And one of the issues with Bluetooth, because of the interference, it does frequency hopping to limit interference with Wi-Fi, RC cards, and the latter, along with microwaves. All right, so now we're gonna go over some select tools for Bluetooth IoT analysis. Granted, there's tools better than this. These 4 tools are directly used, which is why I'm referencing them. You can see that one GitHub project, JADX, it's great at essentially turning Android Java code into, Android APK compiled into Java pseudocode. So you can just directly look at an application right off the Play Store and decompile it and get straight Java code. So it does most of the work for me, that tool all by itself. We have BetterCAP, which is a great tool for interfacing with the Bluetooth chip in general. It'll allow you to make arbitrary write and read commands, allow you to set up what's going to be referred to as a GAT server, or a generic attribute server, which is part of the Bluetooth spec. We're going to go into that a little more in the future. Aurora Store, honestly, the reason why I like Aurora Store, it's essentially a clone of the Play Store, but when you're downloading things, it allows you to get the APK without installing it. So just having access to the APK, you can pick the corresponding version, and oftentimes with issues with at least Android reverse engineering, the version specific is very important. So once again, Wireshark, as I'm sure most of you are familiar with Wireshark, it's going to be our primary tool I use to go over the protocol. All right, so this is actually the result of running BetterCAP. So we're going to focus on two points here. And as I have stated in the bottom text, the GAT, or generic attribute profile, is a protocol that defines how data is exchanged between Bluetooth devices. Once again, it is client server, and the GAT server stores attribute data. So the way I like to look at this is that essentially, if you think about like a network protocol, like for example, like a web server running on port 443, there's a similar interaction with Bluetooth. They're called UUIDs, or unique identifiers. It's essentially a long string of 32 characters reflecting 128 bits. And the Bluetooth specification, like a web server running standard port 443 or port 80, it defines use cases. So for example, you see battery level, and you see 4 characters. That's actually a shortened UUID, where you're only getting essentially 16 bits of the whole long string. When the Bluetooth protocol, for things that are known well, like battery level, those are usually condensed. When you see this long string, this is essentially the specification allowing vendors to create their own unique protocol. So in this case, you see the one that starts with 736.319. In this case, this is actually a Bluetooth blood pressure cuff. And this service allows a few abilities like read and write, along with sending notifications. We're going to go ahead and move forward. And for this particular slide, though, I added some generic information because the device in particular, there is some redacted information. But I'm going to proceed. So once again, we have BetterCAP. If you're looking for like an example of how to run the command, this is stolen directly off their website. This is just literally a screenshot. I would definitely recommend going to BetterCAP and checking out these resources. In this case, the guy listed here is able to unlock a Bluetooth smart lock by just sending a strings of all Fs. And he got the lock to pop. I'm using this as more so just as notes. I'm not going to really go over this, but if you would like to reference it, I recommend going to the site. Another honorable mention is this program called NRF Connect. It's an application that works on Android, iOS, along with desktops. And Nord Semiconductors makes it. They're the same company that produced the chip that was actually on the device. In this case, once again, like BetterCAP, you can create your own Bluetooth servers, and even allows you to set macros where you can do some kind of arbitrary command attempt to fuzz the device, see what kind of responses you get. Great resource. You're not going to really get into the weeds of it, but I just want to leave it up there for reference. And once again, at the end of these slides, you'll see where you can get all this information. So now we have select tools for Bluetooth sniffing. There's a lot of devices. There's the Elysis, Bluetooth Explorer. Probably not even pronouncing that one right, but we looked at slide at 25,000. The thing about Bluetooth is that because the advertising is always done on one of 3 overlapping channels, depending on the device, if you're using a device like the Ubertooth 1, you can only get about 33% of the information that you need. So it's recommended to have 3 Uberteeth for this to work out properly. But in all honesty, Ubertooth 1 worked out best for me. I've never used this device right here, but I'm not paying $25,000 for anything, so no. Ubertooth 1, you can get this on eBay for about $60 flashed to the current firmware, which will save you like enough headache by itself. So Ubertooth 1 is the way to go, and you can still get these $60 fully flashed. That's what I recommend. NRF, once again, they have this Bluetooth dongle pack. There's a lot of stuff. I can't really get into it, but they're Nordic Semiconductors. They know their stuff, and I would definitely recommend using them as a resource. Okay, so we want to talk about Bluetooth sniffing. I will have a demonstration of Bluetooth sniffing. We're going to save that for the end, but I just want to go over a quick concept called the HCI. Bluetooth stack uses this thing called the host controller interface. And the easiest way to looking at it is, this is my Pixel 4a that I'm doing this demonstration on. It will reflect the host. The controller is actually the Bluetooth chip directly on the phone. So you can think about the interface being like a bus for these 2 things. But yeah, the host and controller are oftentimes on the same device. The reason why I bring this up is that if you're trying to do Bluetooth reverse engineering, because of the difficulty in actually doing practical Bluetooth sniffing, it's important to get the information before it's being broadcasted, because you run into 2 issues. Broadcasted Bluetooth data can be encrypted, and it's not going to do much use there. And also, there's a lot of diagnostic information that's sent from the host to the controller that never makes it to the internet. That never makes it over the air. Instructions for setting a long-term or short-term key. So just something to keep in mind, that by pulling what's called the HCI Snoop log, it will allow you to get this information. If you have an Android phone, it's a setting you can enable right now. Just go into your settings menu. If you look up HCI Snoop or HCI Snoop log, you'll be able to immediately start loading this data. The good thing about it is that because it's gathering the information prior to encryption, it can just save you a lot of time. I was slamming my head against the wall for a while, so I don't want you guys to have that experience. So. All right, so here we go. Find random Bluetooth blood pressure monitor. Okay, so the reason why it's random is that although there will be plenty of hints, and I kind of look at it like a visual, like capture the flag challenge. If you're actually able, I have another test if anyone's actually able to determine what device based on enough hints there in the presentation. I don't make it very easy, and also because of a few vulnerabilities I've reported on this device, there's a few vulnerability numbers that are being pended. So this is an official disclosure, but look at this as a sneak peek. It's officially coming out next month. So yeah. All right, so here we go. Lots of stuff on this slide. So now, in this case, we have a Wireshark PCAP, and we've got a lot of stuff going on here. What I'd like to bring everybody's attention to, though, is that Wireshark is great at parsing all this Bluetooth information, and for devices that use defined GET UUIDs, like for example, like there is a measurement for blood pressure that's well defined by the spec. In this case, this device did not use that identifier. If you see unknown is because it can't determine what it is. So just take a look at this. We're going to go further into this. I just like to dump a bunch of information in front. In this case, you see a value column. These are actually strings that were sent from my phone to the blood pressure cuff. And part of this reverse engineering is going to go over what this actually means, so that to make sense of it. And we're gonna go over a few examples. The application in question here, or at least for the vendor makes like about at least 6 products. So there's a lot of code that's meant for different devices. We'll go over that in a second here. But I just wanted to get you looking at the Wireshark PCAP. In this case, I don't know if you can see in the upper left-hand corner, I used a filter called BT-ATT for Bluetooth Attribute. Essentially, by using that filter, you'll get rid of everything that's not actually over the air. That'll be more important as we move forward. So let's keep this moving here. Okay. So now we're still looking at this data. So I spent a lot of time just staring at values, and just staring at it to see if it made sense. And I wasted a lot of time just staring at it. And it didn't start off. This didn't start off very technical. Lots of staring. Eventually, though, we get some insights here, and it can't be said for the rest of it. But we know what some of these values are through a lot of trial and error. And in the future, I'm going to show you how to avoid some of this error, because the information was in the app to make it a lot easier to find. But if you're doing trial and error, you'll eventually realize that getting all these strings, these hexadecimal strings, it turns out, just converting base 16 to base 10 or hexadecimal to what we normally use, we get all the values here that are left in this application. So you see 6F is 111 for systolic and diastolic pressure. We have the pulse rate, mean arterial pressure, and pulse pressure, but all that information was in there, not encrypted. I mean, it's still considered plain text. All right, so we're going to go back to this trial and error. So in this case, what you're seeing is the result of the result of my blood pressure actually being monitored live. So we got the columns. Once again, we see the information that appears over here, like systolic, diastolic pressure. We also see this column to the far right. And the reason why it's changing is because as the pulse is being calculated, those values are changing. So you're basically getting real-time data. So trial and error was me trying to figure out what the rest of it means. And I'm only going to get so far here just trying to stare at it and guess how it could be coded. I hit a brick wall again. So I'm just like, well, trial and error, see this value incrementing or doing something. I think we're getting somewhere. But I eventually decided it's time to look at the app, because I can't spend I spent a ridiculous amount of time just staring, and it was, yeah. All right, so here we go to the app. So now, once again, although I don't think I tried to Google most of the functions, and this information is it's not sitting out there easy to grab, but the reason why I pull up this screenshot right here is that this is actually a function that was pulled out of JetX, called BLE Service. Fortunately, it's called BLE Service, so I didn't have to really think about what it did. Not exactly obfuscated in this situation. What's important, though, is that when I scanned the device with BetterCAP or I used NRF Connect, I looked at those UUIDs and I tried to find it in the source code. So as we see redacted UUIDs, find them in the source code. And like I said, UUIDs are not private. In this case, they are, for this service, all of their devices use the same UUID to reflect write and notify. So these are essentially static, but they're not part of the official BLE specification. All right, so here's where things start getting interesting. So I'm looking at where I got so far, and what I know is that if you see the vertical lines at the top, I got these basically separated like they're arrays, and I stick to what I know. So I still have the information that I got from the app. You know, I see pulse rate is 91, mean arterial pressure is 72. So I'm still looking at this, trying to figure out like what's going on here. So I keep looking at the app and what's in this first position confused me at first. Eventually I found a function called getRequest. And yeah, so we got this getRequest function, and we see these byte arrays that it makes. Now it may not be noticeable right away, but if you look at where we start with that number minus 91, what I quickly notice is that from byte array position 0 through 6 can now be reflected. So essentially this first line from my Google phone to the device that ends at 92, that's essentially a GET request where it's reading a file off the blood pressure monitor. So that minus 91 is, here's things get a little tricky. Apparently in Java, when we get minus numbers, because Java doesn't have unsigned bytes. So the fact that this number is stored as minus 91, it gets the 2 complement version of it. So essentially, minus 91 becomes 91. You invert all the bits, and then you add 1. So that minus 91 is represented. So that's where I get essentially this 165. And honestly, the built-in calculator that comes with Windows was another honorable mention because I spent a lot of time just using that. All right, so we're going to go ahead and move forward so we can explain the rest of this. All right, so now we're going to focus on this byte array position 1. I was still looking at that number 243. You know, we got 243 from F3. So I kept wondering, well, what exactly is it doing? I don't know what 243 is. I kept searching the app until I found 243, and I kind of got a little lucky here. So here we go, 243. We have another function called BLE Command. So now we have a bunch of commands. So at least we know the first part is, you know, my phone is making a request, a blood pressure monitor, making a request. In this case, the request is the read package, 243. But at this point, I'm still not entirely sure that's a coincidence. This app has hundreds of functions, and I'm not entirely sure, so I'm going to move forward to see everything matches up. So we're just going to go ahead and move forward. All right, so now I found some additional code. It actually turned out that this code is actually not for the blood pressure monitor, but for another one of their devices. This oxidizer use a finger. But it gave me important context, though. The context it gave me is this word command. It at least let me know that we're on the right page, that, you know, when I'm looking at this string, it must refer to a command. A difference here, though, is that for byte array position 4, it indicates package number, and the original static byte, it reflects sequence number. I'm not really sure these are entirely the same, but you know, they seem pretty consistent with their products. So we're going to move forward. All right. So now we've got we got the next portion. We got a little squiggly line, the tilde symbol, and essentially when we're looking at this. It's basically acting as a NOT operator, so if we see the 243 represented binary, flip it, we invert the bits, we get 12. So at least it's making sense. Still not 100% sure what it does, but at least it's starting to click here. So, all right, and this is pretty straightforward. Just like in the other function, byte array 3, it's a 0. Why they chose 0, still not 100% sure, but at least it's making sense here. I see 0 up here. At the top, you see 0, 0, so we're getting somewhere. All right. Finally, we've got this last thing, CRC. So CRC is usually cyclic redundancy checks. Devices use this to make sure that data isn't getting corrupted. What's odd about Bluetooth is that although Bluetooth already has its own built-in CRC, because they essentially made a proprietary protocol to exchange information between the smartphone and the device. In their own protocol, they added a CRC check 8, which I thought was interesting. So I used crccalc.com, and yeah, it turned out to be valid. Now, the math behind doing CRC checks, you'll have to ask somebody else about that, but it's handy website here. It let me know that everything was good. All right, so once again, we have a Wireshark filter basic cheat sheet. This is just a quick and dirty cheat sheet. Once again, I mentioned BT attribute. That'll show you what's going over the air. If you see the second one, you'll see it ends in long-term key. That lets you know that you're running at least Bluetooth version 4.0. And if you see a value for long-term key, that it means that the HCI is setting a long-term key, which means that you know it's encrypted. And if you see the second value, just the link key, you know that you're running Bluetooth Classic. But if you don't see these, then you at least know that it's not encrypted, which is great. Because in this case, it wasn't encrypted. So not being encrypted brings us to just a couple issues. I'm going to go ahead and show a demo. I forgot it was the next slide, but I'm going to link this. So if you guys want to go over this again, what's important to make out here, I'm going to probably play this one more time, is that essentially what you're seeing here is you're seeing the Ubertooth following the connection. So you'll have the connection between my phone and the device, and what usually happens is that when a Bluetooth device is sending out advertising requests, it'll advertise on one of those three channels, 37, 38, or 39 in the hour. And then once it completes the pairing process, which in this case the pairing process was kind of flawed because of the lack of encryption. But once the pairing process completes, you'll see one of these fields. It'll say frequency, and you'll see that it's hopping, and that's done after the connection's been established. So right now, the Ubertooth is able to follow the connections across the fact that they're hopping between 36 channels. So that's the magic of the Ubertooth, the fact that it can do this following the connection. And in this case, this is unencrypted data that I was able to get with the Ubertooth. And the main thing it's here to demonstrate is that on this device, the information wasn't encrypted. It was medical adjacent information. So for PII concerns or potential HIPAA violation, I was able to pull it off the air. Whoa, whoops. Technical difficulties here. Few moments. So get a little recap. All right. All right, so another thing that's just worth noting, when you're using JADX to do Android app, like reverse engineering, you're just looking at the app, you'll be surprised what's inside there. In this case, I found hard-coded API keys. And there's limited damage you can do with the Google API key, but you can certainly cost the company a lot of money by having them fetch resources. I also found API keys for their own API because I limited my research to a device that I own and nothing transversing out. I haven't done much poking at it, but like I said, this information is right in the app, and if you can determine what the device it is, you'll have these API keys too to get into some mischief here. So once again, we have some conclusions here, and one of the big conclusions, if there's nothing else to take away, is that there are so many different classes of vulnerability that if your goal is just to find a vulnerability, you'll definitely find one, because there's enough vulnerability. Like I said, but here's a few examples: missing encryption of sensitive data, and use of hard-code credentials. There is a point of concept I'm still working on. I haven't, but I'm pretty sure I see a few buffer overflow examples here. So if anybody, feel free to beat me to it and can identify the device, have at it. But I don't have a working POC yet. So if you want to contact me, you can get these slides on GitHub, and you can find me on LinkedIn. Yeah, any questions?
How long did this process take, start to finish?
I spent an embarrassing amount of time looking over the app, and I'm still not 100% done. There's just so many functions, and just trying to get it to play through my head, it was definitely a challenge. But I spent an embarrassing amount of time on just this presentation, so I appreciate everyone for showing up here.
Years, months?
We're
Weeks?
a month.
1 month? Oh, that's pretty, it's not that bad.
Yes.
Yeah, the devices you were looking at, like
So the FCC website says that they had the spec sheet at 2019. So I'm guessing it's a 2020 device. It's still pretty new device to still be running 4.0. We've got some. There's a lot of insecurity been added. Even 4.2, they added the idea of secure connection. So when when device pairing happens, it is using public key crypto. But even this device, it's relatively new, and even had a brand new chip, and it was still using deprecated versions. So, like most devices I've encountered. Yeah.
Yeah, so when you were running the Wireshark, were you just specifying the Ubertooth directly?
So I was specifying the MAC address of the device, because one of the issues is that oftentimes for Bluetooth devices, you'll notice if you ever look for Bluetooth and you'll see like a bunch of iPhones, oftentimes the vendor will enable like MAC address randomization, kind of like we normally use for Wi-Fi, but you'll see the Bluetooth interfaces. In this case, it didn't change. It had a static MAC address. And another odd thing, though, is that I actually thought it was a randomly generalized MAC address, but then if you do like a vendor lookup, you'll see like the first 6 characters. They're not specified. So it's like they were randomly generating the MAC addresses, but they were burnt on there. So like, yeah, I thought that was interesting. Yes.
If you do run into something that's encrypted, do you have advice for starting to try to poke around at that or figure anything out about that?
When it comes to encryption, Bluetooth is vulnerable to there's a lot of like attacks against Bluetooth. So it really just depends on how weak like the nonce is generated. I think on the top of my head for Bluetooth. I mean, if you happen to have the key, you can get Wireshark to decrypt it if you have the right information. But that's going to be very tricky. But like I said, there's a lot of vulnerable chips. When it comes to Bluetooth, a lot of it seems to be chip specific. I know like ESP32s, they're vulnerable to all classes of attacks. So I would look at the chip and see if there's anything specific. But I've heard of some wild attacks when it comes to Bluetooth. But I don't have anything specifically to detect encrypted. I would say I looked at about 20 devices, and only one of them was encrypted. The Garmin one, I can say Garmin because that's not this device, but the Garmin blood pressure monitor, it is encrypted. So, yeah, and it also, it bypasses some of the shenanigans, but yeah, this was not Garmin.
Okay. I know we want to ask more questions, but our next speaker, we need it on his or her time, so we'll start.
Okay.
If you have any more questions, you can speak with him outside.